Okay, hello students. So in the last lecture, we did your topic of chain rule, and in that topic, we did some of the important questions that are usually asked on the topic of chain rule, and there we can easily see how chain rule is used to solve the find the derivative of such type of functions, because I have earlier told you that the basic use of chain rule is there where the substitution is complicated, or even the functions that are involved are not given in your explicit form. So here you can see you have been given function not in your explicit form, it is given in your implicit form. So this is the actual use of chain rule. So in previous lecture we see how we can use a chain rule to solve such type of problem, and using chain rule, these rule makes the thing easy for us to work out for these type of problem. Similarly, it was another example where we worked for second order derivative. Okay, so next is your topic of directional derivative, a very important topic of your directional derivative. Now see, in the directional derivative, what the basic ideology or thing behind directional derivative is. So first thing, directional derivative, before that let me just start from the first or one variable function y equals to fx. We have dy dx or df by dx, whatever you want to say. It gives a rate change of f or y with respect to x. So this is what you have your first order ordinary derivative, where y is a function of x only or f is a function of x only. So dy dx or df by dx ordinary derivative gives you a rate at which f changes with respect to x. And if say I am saying at some point x naught, that I am looking the derivative at some point x naught with respect to x at point x naught. So this will give you the rate change of f with respect to x at point x naught. Now similarly, we consider that say if function is of two variables. In the one of our lectures we consider function of two variables, and there we have your partial derivative of x and y. We have partial derivative of x and y, partial derivative f. Now the partial derivative f with respect to x gives you the rate change of f with respect to x, or I can also write it as or rate at which f changes with respect to change in the value of x, or rate at which f changes with respect to change in the value of x. So it gives you rate change of f with respect to x when y is fixed at y equals to y naught. So this was the thing we did about your partial derivative f with respect to x, that it gives you rate change of f, that how at which rate f changes with respect to x when y is kept fixed at y equals to y naught. If say we are saying it at some point x naught y naught, if say we are saying it at point x naught y naught, then it is at point, you can simply add that it gives you rate change of at point, or simply let me write it here, not in the last, let me write it here at point, right? Let me write it here. So this gives you rate change of f at point x naught y naught with respect to x when y is kept at value y equals to y naught. Also from here we also have seen that it gives, we have earlier studied about this, that it gives rate change of f in direction of I cap, in the direction of I cap. So this partial derivative f with respect to x give you rate change of f in the direction of I cap or x-axis. Similarly, when we were talking about your partial derivative of f with respect to y at point P naught is say your x naught, y naught, then we see that it was your, it gives rate change, it gives the rate change of f at point P naught, say point is x naught, y naught, with respect to y when x is stepped at value x equals to x naught, and it gives basically a rate change in direction of j cap or y axis. Now, what is the use of telling you all these things in the beginning of your directional derivative? The main thing is that now, if you see at the partial derivative x and partial derivative y, they are giving you the rate change. One is giving you in the direction of y-axis and other is giving you in the direction of x-axis. Say this is your x-plane, x-axis, this is y-axis. However, if we have to find rate change, if we have to find rate change of f with respect to both x and y. This is the main basic concept idea behind directional derivative. Earlier in the partial derivative, we were fixing one of the variable and varying another variable. Okay. Now in directional derivative, what we are looking for, we are saying that now what will be the change or a rate at which f changes, rate of change of f when both x and y are changing. Okay, that is rate change of f with respect to both x and y. That is when both x and y are varying. Now, no variable is fixed, no variable is held constant. Both the variables are changing, both x and y are changing. So, what will now be the rate change in the value of f? That is, now you are changing, or say you are varying in the direction. Say you have this direction. Okay. Now he is not saying that you are, but is the rate change along x-axis or a rate change along y-axis. Now he is saying take any of the arbitrary direction. Take any of the arbitrary direction. What will now be the rate change at a given point of in the value of f? And you have to look in any of the arbitrary direction. So that concept, that thing, that is rate change of f in any direction at any point in any direction, that is when x and y are both varying, that is given by the concept of your directional derivative. So this is the more generalized term for finding the rate change of function fxy in any of the arbitrary directions. Partial derivative of f with respect to x and partial derivative of f with respect to y, they are both the particular cases because they are giving you rate change in one of the particular direction. One is giving you in the direction of x-axis, other is giving you in the direction of y-axis. However, directional derivative will be more generalized case where you can find the rate change of f at any point in any of the arbitrary direction. So, directional derivative, let me just write. So if we want to find rate at which fxy changes with respect to, or simply let me write here, rate at which fxy changes in the, or just let me write it here at point x naught, y naught, So if we want to find the rate at which fxy changes at point x0 y0 in the in the direction in the direction of any arbitrary unit vector, u vector is equal to u1i plus u2j. So what is this unit vector? You know very well that direction is usually given by the unit vector. So that is, it is simply representing, that is, change in value of x and y simultaneously. The direction of unit vector means that both x and y are changing, because now you have both I component and j component. So both the components are there available, not only I and not only j, both are present. So basically x is also varying and y is also varying. So instead of saying that we are finding the rate change of f with respect to the change in the value of both x and y simultaneously, he is saying that we are finding the rate change in direction of any unit vector u. That is what it simply means, that x and y are varying. So if we want to find the rate at which fxy changes at point x0 in the direction of any unit vector u, then it will be given by directional derivative. It will be given by the directional derivative of fxy at point t0 here. So this is the concept of directional derivative that will give you the rate change of f with respect to your, or in the direction of unit vector, or with respect to change in the value of both x and y simultaneously. Now here we have a definition, proper definition of directional derivative. We have a proper definition of directional derivative that we will be doing later. Okay, so now we are now will be doing the definition, not the definition of directional derivative. First we will see how we can find out the directional derivative. I have just given you an idea about what the directional derivative actually are. Its grammatical interpretation and the definition that we will be doing later. So regarding grammatical interpretation, I must say here that as we have done this one, ordinary derivative, you know, this gives you the tangent. Okay, this dy dx gives you the slope of the tangent at the given point, x0, slope of the tangent. Similarly, when we did this partial derivative of f with respect to x, let me write it here, with this y dy dx. So here it gives you slope of tangent, or at x0, slope of tangent at point x0. Similarly, when we did this one, I am just considering here only the point partial derivative f with respect to x, not with respect to y, because that is similar, you can explain that. Partial derivative f with respect to x at point x0 y0 gives you the slope of tangent to the curve fx y0, that is obtained, how you obtain, that is obtained by the intersection of surface fxy, of the surface fxy, and plane y equals to y0. The plane that goes from line y equals to y0 has the plane y equals to y0 that is running through the line y equals to y0. So the intersection of surface and plane gives you the curve fx y0. So slope of the tangent to the curve, this one, at point x naught, y naught, z naught. Here z naught is f x naught, y naught. Yes, this is. So this point is basically on the surface. Point x naught, y naught, z naught is on the surface, and at that point, the slope of the tangent to the curve, this curve, is basically giving you the partial derivative f with respect to x. Similarly, the directional derivative of fxy, directional derivative of fxy at x naught, y naught, is simply also giving you the slope of the tangent. This we will discuss in the next lecture. So it is similar to the concept of partial derivative, okay, because this is more generalized concept of partial derivative. Partial derivative are basically the particular case of directional derivative that gives you rate change in any other direction, directional derivative. So directional derivative is basically same thing. It will also give you the slope of the tangent to the curve this one, but however here plane will be not y equals to y naught. This will not be the plane. Here plane is parallel to unit vector u passing through x naught, y naught. Yes, so only difference for the directional derivative is that the curve that you obtained fx comma y naught, or the curve that you will be obtaining there, will be obtained from the intersection of the surface with the plane that is parallel to that unit vector u. So this is only a difference of directional derivative. Geometric, it will be giving same thing that we have taken from your partial derivative. Now, before going for the formula that how we can find the directional derivative, here we are looking for the components that are used in that formula. First is your gradient. So for the gradient, you know very well what is gradient. The gradient vector of fxy at a point. Now your gradient, because this is going to be used in the mathematical formula for finding directional derivative, at point P naught is a vector given by grad f, or by this formula we usually denote it by grad f or del f, and this is the partial derivative of f with respect to x phi cap, partial derivative of f with respect to y j cap. So basically gradient is the derivative of multivariable function. In single variable you have dy dx. However, when a function has more than one variable, its derivative is given by your gradient. So gradient f is basically your this vector, and important point regarding gradient is that it always points in the direction of greatest or maximum increase of function at a given point. That is, at a given point, whatever the point x naught, y naught is, it will always, if you find the gradient at the given point, gradient is given by this one. You put the value of point x naught, y naught here. So the vector that you will get at that point will always point in the direction in which the function has greatest increase. So this gradient f is basically giving you the vector or the direction in which there is maximum increase or greatest increase in the value of f. Now coming to the formula that gives you how to find the directional derivative. So if the partial derivative, so here is the theorem that gives you formula for finding a directional derivative. If the partial derivative of fxy are defined at P naught, then the directional derivative of fxy at point P naught in the direction of, because we will always be looking in some direction, in the direction of unit vector u is given by, yes, it is denoted by d in the footer u f p naught. So this is how we denote your directional derivative of function f with respect to, the directional derivative of f in the direction of unit vector u. So this is how we denote your directional derivative. And then also we denote, the formula is p naught dot u. That is the, you can find the directional derivative of function at a given point p naught by finding the dot product of gradient of f at p naught and unit vector u, the direction in which we are looking for the rate change. So this is a formula that we are going to use for our mathematical calculations to find the gradient. That is the scalar product or dot product of the gradient of the function at the given point and the unit vector. So let us see how we can find the results using this formula. The question first is find the derivative. Sometimes instead of saying directional derivative, he usually says derivative. So find the derivative of function at point P naught in the direction of A at point P naught, where fxy is equal to 2xy minus 3y square. Point is your 5, 5, and vector A is 4i plus 3j. Yes. So this is the basically question given. Function is given, point is given, vector A is also given, where you can find the rate change of f, directional derivative of f. So directional derivative of f with respect to, in the direction of unit vector u at point P naught is noted by this notation, and it is the scalar product or dot product of gradient and unit vector. Yes, here it is. So now first you need to find the gradient. Of f. So gradient of f, from here it is your fxy. This is gradient of f is del f del x I cap, derivative of f with respect to y j cap. So this gives you, with respect to x, this gives you 2y, yes, I cap, plus y. Y is your 2x minus 6y j cap. And hence, if you find this value at 0.55, this gives you 10i plus 10 minus this is your minus 20. This is minus 20 j. Yes, so here you get the first term, that is a gradient of function at point P naught, 0.55. So here you get the gradient. Now we come to the unit vector. Unit vector is given by, the vector is A. So here usually most of the time we make a mistake that we take the vector as such. No, we have to here use the unit vector, because in the statement you have the dot product of gradient with unit vector. So vector is A, that is 4i plus 3j. So unit vector is your, this vector divided by its mod. So this gives you 1 upon 5, 4i plus 3j. Yes, this is. So this is your 3. Hence gradient vector, hence your directional derivative at point P naught, that was by formula equals to this one, is equals to, your gradient is your 10i minus 20j, into, dot product 4i plus 3j. So this gives you 40 minus 60 upon 5, so this is minus 4. So basically this tells you that the function fxy at point p0, function fxy, that is equals to 2xy minus 3y square. Point p0 is 5, 5. Vector a is your 4i plus 3j. So this result tells you that at point 55, this function fxy has a rate change in the direction of this vector, the direction of this vector equals to minus 4. That is, it is changing at the rate of minus 4 in the direction of this unit vector at point 55. So this directional derivative is basically giving you the rate at which function changes at a given point in the particular direction. So it can be positive, it can be negative. Okay, so it can also be 0 in some of the cases that we will see in the next of our coming lectures. So here the rate is minus 4. So this completes your first example. Now another example. Here again the same question. Fx, y, z is, function is now this one. Point is your this one, and vector is your this one. Vector is your this one. So again you have to find the directional derivative. So directional derivative is given by this formula dot u. So in some of the books he is writing simply u or u vector. You can use any of the notation. Either you can write u or u vector. It depends upon you. So now gradient of f, here it is del f del x I del f del y j del f del z k. So this gives you 3ex cos yz fx I cap, partial derivative is equal to y, 3ex z sin yz j, and then with respect to z it is again 3x y sin yz k cap. This is, so here this gives you the gradient of function, and at the given point p0 it reduces to 3i, and yes, rest of the terms are 0. So this reduces to only 3i. You can see here. And putting value x, y, z equals to 0, you get the gradient at the given point 3i. Also other thing you need to find u, that is a vector upon its magnitude, that is 2i plus j minus 2k, and this gives you 4 plus 1 plus 4, so 1 by 3 2i plus j minus 2k. Okay, hence your directional derivative at the given point in the direction of given unit vector is equal to 3i was your gradient value, and then unit vector is your 2i plus j minus 2k. So this gives you 2. This gives you 2. So basically the rate at which the function fx is changing at point this 0, 0, 0 in the direction of vector 2i plus j minus 2k is equal to 2. So at this point rate change is 2. So this gives you the directional derivative of the given function at the given point. So now I am coming to the properties of your directional derivative, but before that I have here definition of directional derivative, definition of your directional derivative. So now here in this case, let let fxy. Now I am giving you the definition of, because the formula that we have used is a basic we basically use to find the directional derivative. Okay, the actual definition of directional derivative is here. Let fxy be defined throughout a region R, in the xy plane. P naught x naught y naught is a point in R, and U is a unit vector, then the rate change of f at P naught in the direction of U is given by we are not going for the derivation of this theorem result, we are just stating it as such, is given by df by ds u comma p naught, or simply du f p naught. These are same notation. Limit s tending to 0 f x naught plus s u1 comma y naught plus s u2 minus f x naught comma y naught upon s. Here s represents, where s is a parameter that represents or measures, that is a more appropriate word, measures arc length from P naught in direction of U. Yes, S is basically a parameter that measures the arc length from point P naught in the direction of U. So this is the formula. Let me write it here properly. df by ds in the direction of U at point P naught is limit s tending to 0 f x naught plus s u1 y naught plus s u2 minus f x naught y naught upon s. Yes, I could add this also, provided limit exists. This gives you the actual definition of the directional derivative of the function at the given point in the direction of unit vector u. So we are not here giving the derivation of this your statement, the definition, but simply for your just, because we are, let me just first do an example, because it's geometrical interpretation and all those things we will do it later. I just told you about the idea of a little bit about geometrical interpretation, that it also gives you directional derivative is simply again the slope of the tangent. But here the difference is that the curve that you obtain from the intersection of surface and plane parallel to that unit vector. Earlier in the partial derivative, the plane was in partial derivative x, it was plane y equals to y naught. In the partial derivative f with respect to y, plane was x equals to x naught. But here the plane was, it will be like that will pass from point x naught y naught, and it will be parallel to unit vector u. So before going for the geometrical interpretation, let me do the question with this definition. Find the derivative of fxy at point, this one, in the direction of unit vector, u is equals to under root I under root j, u's definition, use definition of directional derivative to solve. Okay. So you have to find the directional derivative of this function at given point in the direction of this unit vector. Okay. So by definition, you have directional derivative. Either you write like this, anything. It is limit s tending to 0, f x naught, f u1, y naught, f u2, minus f x naught, y naught upon x. So this gives you limit s tending to 0, f, yes, point x naught, y naught, it is given to be 1 to unit vector u1i plus u2j is given to be this one. So this is the all input that is given in the question. So I just need to put the values here. This is 1 plus s u1 is under root 2, comma 1 plus under root 2, yes, and then this is your, y naught is 2, s is as such, and u naught is 1 under root 2. Yes, it is fine. Minus f x naught, y naught, 1, 2 upon s. Yes, this is. So this gives you limit s tending to 0, whereas your fxy is given by the formula x square plus xy. So this function, when you use from it fxy, you will get 1 plus s under root 2 the whole square plus 1 plus s under root 2 into 2 plus s under root 2. Let me write it properly. This is okay. So you get it from here, minus f12, 1 का square plus 1 into 2. Yes, 1 into 2. So this gives you upon whole divided by x. Now when you solve it, rearrange the term, this gives you limit s tend to 0. I am writing it in the proper form, 1 plus s square plus 2, 2s plus under root 2, 2 plus 3s under root 2 plus s square upon 2 minus 3 divided by s. So this is what you will get when you expand the terms here and multiply this. You get finally this term 1 plus s square by 2. Let me just check. 2s upon under root 2, 2 plus 3s, this is 3s, and finally when you are done with it, you will get here s plus, s plus 5 upon under root 2. You will get here 5 upon under root 2. So I am just multiplying this, taking this s with numerator also. So finally you will get this thing, and this will now reduce to value 5 upon under root 2. Yes. Or if you want to write it properly, you can also write s square 5s upon under root 2 upon s. Yes, this is from here it comes s plus 5 upon under root 2. Yes, so this is the directional derivative in case you are using the definition. So this is how we use the definition to find the directional derivative, and this value in this case comes out to be 5 under root 2. Okay, so for today's lecture I think this is enough, and in the next lecture we will consider the properties of directional derivative, and also if we get time we will also do the geometrical interpretation of directional derivative. Okay, till then, thanks a lot.